Good morning, lovers of natural history. Bob Ellis here with another episode of Notes from the Field. And today we're just outside of Camp Verde, Arizona, and very near West Clear Creek. You can see it there in the distance. And we're up on a hillside. We being James, our collection manager, and myself. And we decided to come out to this location because you can see all around us this wonderful shrubland. And we're interested in thinking about these shrubs in the context of one of those master abiotic factors. In an earlier episode of Notes from the Field, we thought about temperature and moisture or precipitation sort of being the gatekeepers to the landscape. And at that time I mentioned that there was one other gatekeeper, and that gatekeeper is our nutrients. And so today we want to think a lot about nutrients and how they paint the landscape as well. So, what do you mean by nutrients and nutrient availability? Well, there are 9 essential elements that are macronutrients for all plant life. Let's see if we can count them off. Carbon, hydrogen, oxygen, magnesium, phosphorus, sulfur, nitrogen, calcium, and potassium. Of those 9 different elements that are essential for all plant life, there are only two of those 9 that end up being limiting factors. And that means simply that they restrict either a species' presence or abundance. And so you might be wondering, well, Bob, why is it that we're just focused on plants? Well, it's probably pretty clear to most folks out there that these plant nutrients are then transferred to those herbivores that eat the plants, and then subsequently the carnivores that eat the herbivores. So these essential elements are fundamental in not only painting this landscape from the floristic perspective, but also for the fauna. Now we're down in that wash that you can see from the shot up there on that hillside, and you're probably wondering, well, Bob, of those 9 essential macronutrients that you mentioned that all plant life and subsequently all life needs, what are the 2 that are limiting factors, not that available? Paint the landscape, produce patterns that naturalists can suss out. Well, that's nitrogen and phosphorus, N and P. So if you look at that hillside, all you see are these spiny shrubs and a few cacti. Here's the deal. Though every one of those spiny little shrubs and many of the shrubs and trees that we're walking past in this wash are in a family, and that family is the bean family, also known as Fabaceae, or for folks who took botany back in the day, Leguminosae, the legumes, the beans. Now, there's a reason for their dominance, and that reason is tied to their ability to extract nitrogen from the environment, whereas many other plants cannot do that. So it's a fascinating story that is a part of the pattern out here that will enhance your understanding of natural history if you just kind of have a sense of how it plays out. So why is nitrogen such a limiting factor when it comes to nutrients? Why is nitrogen a gatekeeper? Well, once again, it's one of those essential elements. All life must have nitrogen. And here is the weird thing. We are constantly bathed in nitrogen. Our atmosphere is 3/4 nitrogen. But the thing is that nitrogen is one of these compounds. It's an element that loves itself. It is engaged in malignant self-love. It is a narcissist because it only or really loves to bind with itself. So the molecule N2, which is 75-78% of our atmosphere, is essentially an inert gas. It is unavailable to all life, and yet it is absolutely required for many life processes. The bean family has brokered a deal with bacteria. And of course, they really didn't broker a deal with bacteria. This is a beautiful story of evolution. That there is a relationship, and that simply means a symbiotic relationship where both organisms benefit, has developed over a vast reach of time between a genera of bacteria called Rhizobium and the bean and plants in the bean family. And here's the deal. The bacteria are the beneficiaries of a sweet place to live in the root of these nodules, and in return of getting a sweet place to live and a lot of nutrients, the bacteria do something that no other organisms on the planet can do, and that is muckle apart nitrogen. That very, very powerful diatomic, actually is a triple bond that holds that molecule together, and they do this with an enzyme called nitrogenase. And bacteria invented nitrogenase roughly 2 billion years ago. So the plant gets the benefit of nitrogen in a usable form, and the bacteria get the benefit of glucose and a nice place to live. It's an expensive process for the plant. It takes roughly 10 grams of glucose to make 1 gram of usable nitrogen. And so bacteria have been busy for a long time figuring out these processes that humans only very recently figured out how to do. In 1918, a German fellow with the last name of Haber received the Nobel Prize for Chemistry for figuring out how to break apart atmospheric nitrogen and then convert it into a usable form for artificial fertilizers. And then in 1932, a German fellow with the last name of Bosch invented a way to produce that on an industrial scale, and that is now known as the Haber-Bosch process. Bacteria figured that out 2 billion years ago. So this very pattern of this mutualistic relationship paints that hillside. Look at the hillside. What do you see there? Nothing but bean plants. Fabaceae is representing because they're able to grow in this nutrient-deficient environment because they have access to this mutualistic relationship in their roots with bacteria. So this is a pattern that is discernible once you have the knowledge. Now, the other element that's a limiting factor that I mentioned earlier is phosphorus. Phosphorus is unlike nitrogen in that nitrogen is fixed. 90% of nitrogen is fixed biologically. So you might be wondering, where's that other 10% come from? Well, here's a weird story. Lightning fixes the remaining 10% of nitrogen, meaning that whenever a lightning strike moves through the atmosphere, it converts diatomic nitrogen to other compounds like nitrites, nitrates, ammonia, just because it has that tremendous power to break apart that bond, and then that nitrogen falls to the earth. Phosphorus, however, is on a one-way path to the ocean, and it is limiting in a large degree because it is tightly tied up in all systems. So calcium phosphate is the typical kind of compound that plants can use, and it is just eroded out of rock formations. So there's no atmospheric component to that limiting factor, and there's no biological fixation. So it is, if it's there, it's there. If it's not, it's just organisms have to evolve different mechanisms for kind of being able to operate on a low budget of phosphorus. Let's just walk on down to the stream, and maybe what we can do is think a little bit about our neighborhood nitrogen fixers here and point out one or two. You know, that's one of the things that I always do whenever I walk into a landscape from a natural history perspective, and I first want to know who are the fixers out here. And it's sometimes an interesting assemblage, but almost always it's something from the bean family being able to take that nitrogen from the atmosphere and then convert it into plant growth. And then that plant growth subsequently decomposes and allows nitrogen that is usable by other organisms, other plants, becomes available. The interesting thing, though, is that nitrogen isn't always found by plants because there are bacteria that interject themselves into the process in a way that captures the decomposing leaf nitrogen that it has been made available, and they cycle it through this whole kind of food chain of bacteria using nitrogen, ending up in a way that nitrogen is pulled apart from oxygen or hydrogen, the other elements that it's bound with, and returns to its N2 state, goes back up in the atmosphere. So it's just this fascinating process mediated by bacteria from start to finish. Here's one of them. Here's one of the fixtures in our neighborhood. And once again, I always like to go around and go, okay, what's doing the fixation out here? And this larger tree is a mesquite tree, Prosopis velutina, velvet mesquite, really common plant in the Southwest, and it's doing a heavy load of fixation. So here's another fixer, and gosh, sure looks like a bean to me. And so this is an acacia tree, and I think the genus is acacia. That's kind of convenient when that happens. And the species is constricta, so acacia constrictor, another fixer. Hey, we finally made it down to the creek side, and there's a couple of reasons that I wanted to come down here. The first reason is it's a beautiful place. West Clear Creek is one of the most beautiful places in the Mogollon Highlands. And then the second reason was I wanted to make sure that I wasn't giving you all a false impression about nitrogen fixation. You know, we walked through those uplands, those dry, nutrient-deficient uplands, and I didn't want you thinking that that was the only place where nitrogen fixation could happen. And I've only talked about rhizobium as the symbiont in that nitrogen fixation situation. And I only talked about the bean family. Let me tell you that nitrogen fixation can happen in a number of settings with a number of species. And so down here is a great example of that. These gray trunk tall trees that stretch in a line down the creek are Arizona alders, scientific name Alnus oblongifolia. They're in the beech family, and they are nitrogen fixers right by the stream. They have a symbiont that is not the bacteria rhizobium. It is in a different genus. As a matter of fact, it's a way different group. It's Actinomycetes, and the genus is Frankia. Same kind of situation as in the uplands. The bacteria captures nitrogen, converts it to a usable form, and the plant pays the bacteria in glucose. And so whenever you go out into the landscapes that you visit or the places where you live, remember that there are 9 different families of nitrogen fixers that are not beans. Here at the Natural History Institute, we really appreciate you going on this walk with us today to talk about nitrogen fixation and how that's one of those master abiotic factors that's painting the landscape. You know what, if you enjoyed this little trip with us, you do me a couple of favors, one of which is to go ahead down there and just smash that subscribe button. And the other thing you could do is go over to our website, naturalhistoryinstitute.org, and check out some of the stuff that we have on there. I think you might be interested. And you know what? If you really like what we're doing, go ahead and hit that donate button, because we're a not-for-profit that's interested in revitalizing the practice of natural history. So thanks again, and look forward to seeing you later.